accuracy and precision. And you probably have seen these diagrams. So the ideal case, obviously, is this one here, where you are accurate. That means on target, you are exactly getting what you're supposed to get. And precision means the variability. So in a way, accuracy and precision gives us a little bit of information that we already dealt with. You can think of the accuracy as being the mean of the measurements. The mean as in how close it is to the real, true value that can be measured by everybody else in the world. So that's the mean. The precision is how far spread out the measurements are. So that would be more or less reflected by the measures of divergence, so variance and standard deviation, and also the standard error of the mean. So these are the two things. What is reproducibility? There's a third one. Accuracy, precision, and reproducibility. Reproducibility would be if you did this experiment, let's say, on another day, exactly the same experiment, you would get the same result. So, you could add another dimension to this graph, if you like, and say, if I do this experiment on Tuesday, and let's say I get this result here, this one here. It is inaccurate. It means there is an error in it. Maybe somebody forgot to put the tip on the pipette. Yeah? But the spread is not very big. So it's inaccurate, but it's precise. Now I do this experiment next day, on Wednesday, and on Thursday, and I get exactly this one here again. Yeah? Because I still make the same mistake. There's still systematic error. It means, in this case, it is inaccurate, but precise and reproducible. And obviously, if we do measurements in science, we want it to be actually this one here. We want it to be accurate, precise, and reproducible. That would be the ideal thing. And obviously, as you can see here, if you just have one dart that you throw at this board, you would get only 1 point. This 1 point, in theory, could tell you how close you are to the expected one. So it could tell you something about the accuracy, but it wouldn't tell you anything about the precision. That is why in science we usually do the experiments not as a singular event, but in multiples. Usually you do them in triplicates. So you do the experiment 3 times, so at least you get a little bit of precision in it, or you can see what the spread is. Yeah? So that's why we do these experiments usually in triplicates. Not because it's a sort of occupational therapy for you guys, and we can't think of anything else to do with you. It's just simply this is good practice because it gives you the precision. When you do, let's say, postgraduate studies, or in your final year when you do your lab-based project in the final year, your supervisor will even be so mean and tell you to do exactly the same experiment on 2 different days to see whether it is reproducible. Yeah? If it's not, okay, let's go back to the drawing board and see where we made mistakes. If it is, for example, if it looks like something like that, your results here, this one here, inaccurate and precise, then we know that there is a systematic error in it, which we need to find. Usually it is somebody made up a stock solution the wrong way or something. Yeah? If it is something like that here, accurate and imprecise, this usually indicates human error. And this is not necessarily your fault. It could be that it's very tricky to do exactly the same thing all the time. So with this grid, if you like, you can find out what's going on with your experiment. That's why we do these things. Does that make sense? Right. Now, in this experiment on Tuesday, my voice is going, you were asked to calculate the mean and usually people didn't have a massive problem with that. You were also asked to calculate did I ask you to calculate the variance? Probably. The standard deviation, but for the standard deviation, you would have to have the variance anyway. And usually people got this all right. So you had to do the standard deviation, where you took your first measurement, and I call that x1, minus the mean, you squared it, plus then you took your second measurement, I call that x2, minus the mean, squared it, and then the third measurement, minus the mean, you squared it. And because these were your data, this is the entire population of the data that you collected, you divided it by 3, that's by n, because you had 3 data points. And for the standard deviation, you just simply took the square root of that. Yeah? It wasn't terribly exciting, but it gave you a little bit of practice how to do these things. Some people came to me and said, I'm utterly, utterly disappointed because something went wrong in my experiment. My standard deviation is 0. Okay, is that bad or good? It's good, isn't it? Because if it is 0, there is no spread amongst the data. It is a little bit like when you go to the dartboard back. It is you hit bullseye here 3 times exactly in the same point. Wow, that's bloody good. So what you want to achieve really with these things, with the standard deviations and variance and standard error of the mean, is you want them to be as small as possible. That is what should get you excited. Yeah? Don't worry about it if it is 0. Worry about it if it is large. Then you have a problem. You then were asked to draw the graph, and most people got this right. So here are your axes, here are the volume that you pipetted, and that was in milliliter. Don't forget, you need to label your axes. You need to put units on. And here was the weight. And that was usually measured in gram. 1, 2, 3. 1, 2, 3. And what you should have got, in this case, should have been a fairly straight line. Yeah? Did it give you a straight line? If you get something like that, what do you do with that? What shall we do if you do a measurement where you expect a straight line and you get something like that? Sorry? You repeat it, exactly. It is, some people say, oh, well, actually, we could do a line of best fit. Whatever this is, a best fit. We will discuss that in one of the next few lectures. So they try to do something along the line of something like that. That would be the best fit. But in this case, I don't think that would reflect the whole thing accurately. I would just simply repeat this experiment and see, do I still get this? Have I checked everything? Do I still get this? If I still get this, then I do it again and look at the spread, because it could be that there's something really weird going on. And in life, weird isn't good. In science, weird is exciting, because there is something that is not what you expect. And that gets really sexy. What you then also can do in graphs like this is you can put in your standard deviation. So, for example, you've calculated the standard deviation for this thing here. So that was 3.0 gram. And you calculated the standard deviation as, I just make something up. Let's say standard deviation was 0.3 gram. Yeah? And what you can do now is you can say, okay, I take one standard deviation above and one standard deviation below my number. So this would be, let's see if I've got a nice color here. This would be, here's 3, that would be 3.3 here, that is one standard deviation. And another standard deviation below, that would be 2.7. And I can indicate that here with what is called an error bar. This error bar shows me how big the spread is. So I have, with a graph like that, I have immediately the mean, that's this cross thing, and also the precision in it with the error bar. And in one of the following lectures, I will show you actually how you do that on a computer in Excel. Has everybody done that in Excel with error bars? Few people, but not all of you, so it's definitely worth revising that. Okay? So that's what you would usually find in journal articles where people indicate this is what the error was. Does that make sense? Any questions? So what we want to train you is whenever you repeat any experiments or do them in triplicate or something like that, second nature must be to you, calculate the mean, calculate the standard deviation. That must be automatic. I expect that from you. If you do something in triplicates or higher plicates, more often you do this calculation. Yeah? Fantastic. Right, you then did the experiment with the paranitrophenol. And you measured the concentration of this paranitrophenol solution. We didn't give you the expected absorbance because we didn't find the exact extinction coefficient, but it's not a big deal. It was just for you to see how a spectrophotometer works, and yesterday we did, obviously, the theory behind it. And what you actually did was you had this compound, paranitrophenol. You actually used it under conditions where this proton here wasn't attached to the molecule. And we will discuss that then. We will start to discuss that on Monday when we start to talk about acids and bases and things like that. And this compound actually absorbed light at, can you remember? 405 nanometers, exactly. So here you shone light through the cuvette, and the substance, depending on the concentration, absorbed light hugely or not so massively. Yeah? But it showed you the working of a spectrophotometer and also how the principle of the Beer-Lambert law actually works. Yeah? Got that? You also used a protein, this bovine serum albumin, and you used light at 280 nanometers. Now, this is light that you wouldn't be able to see. This is ultraviolet light, UV light. You can't see that. You can only feel that in terms of in the form of skin cancer. So if you expose yourself to 280 nanometers for a long time, you will get redness, soreness, and if it is too long, then it will damage your DNA and it can cause skin cancer. Also, I think I made a mistake yesterday. Proteins frequently, or very often, I should say, absorb light at 280 nanometers. Why is that? Well, they have 3 amino acids which have an aromatic ring. An aromatic ring usually means something like that in it. Anyone know these 3 amino acids that contain? You haven't done that in Bi300, I guess. You have? You have done it. Okay, 3 amino acids with an aromatic ring. That is regrettable. What would you like to call them?
Ring 1, ring 2, ring 3.
Yeah, I think you beat me here. I can't argue with that. Anyone? 3 amino acids with an aromatic ring. Tryptophan, yes. That's abbreviated with a W because there's no W in tryptophan. Phenylalanine, alanine, that's F, yes, exactly. One more. That's the W. Yes, and that's the tyrosine. These are the 3 amino acids that have an aromatic ring in it. And these aromatic rings can absorb light at 280 nanometers. Okay? Makes sense? So, but it depends how many of these amino acids a protein contains. So, for example, if a protein doesn't contain any of these 3 amino acids, it would hardly at all absorb light at 280 nanometers. The light would just simply shoot through. On the other hand, if a protein contains lots of tryptophan residues, it will very, very strongly absorb light at 280 nanometers. So measuring protein concentrations with ultraviolet light is good as long as the protein has the right amino acids. Here's another question for you. You remember that in this particular experiment, you used a cuvette with a black dot on it. Yeah? Or at least you should have used that. Do you know what's the difference between this cuvette and this cuvette that you used for the paranitrophenol? Both were made of plastic. Sorry? Not the surface area, but it's a good thinking. That's a very good thinking. Actually, the issue is that these plastic cuvettes usually absorb UV light. Right? So, UV absorbent. Now imagine if you put this cuvette into a 280 nanometer, what would happen? The cuvette would absorb everything. It would be basically like a black box. You couldn't measure your BSA. So in this case, you have to use a specific plastic that does not absorb the UV light. Let the job be done by the protein. So you have to be careful when you do measure things. You always want to use the right cuvette. A UV cuvette, in previous years where this plastic hadn't been developed, this UV non-absorbent, in years where this is a fairly new thing, you had to use glass cuvettes. But glass cuvettes also absorb UV light. That's why you don't get a sunburn when you are indoors and sun is going through the window. So you had to use special glass, a quartz glass. Quartz doesn't absorb UV light. And these cuvettes were 10 pounds a pop. So with 220 students, i.e. 440 hands, you can imagine that this got a little bit expensive after a while when these quartz cuvettes got dropped. And now, luckily, they are much cheaper because they are plastic, special plastic. Okay, so we got this. Yeah? Happy with that? And then you were asked to do some calculations. How many people have done the calculations? Hands up. Oh, that's quite a number. I better not ask how many people haven't done them, because I don't want to embarrass them. So what I want to do very quickly is I want to whiz through these calculations. So for the first question, it asks you what is the molar concentration of the 10 milligram per milliliter solution. So we've been asked for the molar concentration, which means mole per liter. And a lot of people have expressed concerns with this concentration thing. And what I want to point out again, it is a concentration is an amount, and this amount can be either in mole or in grams. Amount per volume. And the volume usually is liters. Yeah? So what we do is we convert one concentration into another concentration here. And so what we want to do in this case is, bless you, we want, and I do it with the dimensional analysis again, what's the unit that we want? Mole per liter. So, do we have mole anywhere given? Explicitly or implicitly? Yep, you're absolutely right. We have 66,000, and that should actually read gram per mole. Yep? So there is the mole in it. So if you see a number like that, where it says the relative molecular mass, this is usually given without units, which I think is bad. But if you see molar mass or molecular mass, you know that this usually is in gram per mole. So we have mole there. So I write the mole divided by 66,000 gram. Yeah? And the mole is good. That is what we want, but the gram has to go. So we have to come up with a creative idea where we cancel it out. Do we have gram anywhere else? Yes, we have 10 times, and now we have milli, which is, yep, 10 to the minus 3 gram per milliliter, which is 1 times 10 to the minus 3 liter. What happens to the gram? They cancel each other out, and I have left 10 times 10 to the minus 3 mole divided by 66,000 times 10 to the minus 3 liter. Well, I can cancel that out, the 10 to the minus 3. And I get, anyone? 1.5
times 10 to the minus 4.
To the minus 4. What is the unit? What was the unit? Molar. So mole per liter, that's the same thing. Yeah? Happy with that? Simples. I hope nobody calls me Alexander. Okay, how many moles of BSA are there in 3 milliliter of a 1 milligram per milliliter solution? Again, we use the information from up there. What are we looking for? Mole. Exactly. So, do we have mole anywhere? Yes, we've got that in the 66,000. So we have mole divided by 66,000 gram. Mole is good. Gram is not good. How do we get rid of the gram? Very easy. We just simply use the 1 times 10 to the minus 3 gram per 1 times 10 to the minus 3 liters. Yeah? So the grams cancel out. Now we've got the problem with the liter. We don't want the liter there. Can we cancel that with something else out? Can we? Yes, we can. Bob the Builder or Barack Obama. So this would be, have we got liters anywhere else? 3 times 10 to the minus 3 liters. You see the liter cancel out. So I just have to whack that into my calculator. And I get, what do I get? Do I get anything? I got 4.55 times, sorry? 10 to the minus 8 mole, exactly. Yeah? Very simple dimensional analysis. You don't have to do anything. You just have to write things down. If I have time over the weekend, I will do a couple of videos where I show you other ways how you can do that if you are more familiar to that. But for me, dimensional analysis is the answer to life, universe, and everything. Right, what else have we got? Oh yeah, what is the percentage concentration, weight per volume, of the 10 milligram per milliliter solution? So we've got 10 milligram per milliliter. Yeah? We know percentage means actually gram per 100 milliliter. That's percentage. So all we need to do really is we have to convert this milligram to milliliter into gram per 100 milliliter. So all we need to do is we multiply, we extend this fraction by 100 here, by 100 here. Because now then we get 100 milliliter in the denominator. That is exactly what we want. So what we have is 10 milligram times 100 divided by 100 milliliter. What is 10 times 100 milligrams? Bless you, it's 1,000 milligrams. 1,000 milligrams is 1 gram. So that's a 1 gram per 100 milliliter. And that is, bless you, is 1%. Again, not terribly difficult if, if you know what to do. Nothing is difficult if you know what to do. Okay? Happy with that? Determine the volume of 200 micromolar BSA required to make 5 milliliter of a 25 micromolar solution. Whenever you have a volume and a concentration, then you can assume this is a working solution. And this here would be the stock solution. Okay? So, you can either use this C1V1 that some people are familiar with, or you can go straight in for the kill. And remember the guy who goes to the pharmacist, where the doctor says, give that guy the working solution. So give that guy 5 milliliter of a 25 micromolar solution. And the pharmacist says, sorry, we only have a stock solution, and that is 200 micromolar. Yeah? You see the concentrations cancel out. We are left with milliliter with a volume, and that's exactly what we want. So, if you do this calculation, you get, what do you get? 0.625 milliliter, exactly. So, what the pharmacist has to do is give the guy 0.625 milliliter of the stock in 3.375 milliliter of, say, water or so. Because that then gives the 5 milliliter. Then we do it like that. We do 4.375. I just try to cheat the customer. Give them less. Okay, you got the principle of that? Is again fairly straightforward. And let's have a look at the last one. Now that's a little bit interesting, the last one. What is the concentration made by mixing 3 milliliters of a 10 micromolar solution and 1 milliliter of a 30 micromolar solution? Hey, life isn't fair, because so far what we have done is we just diluted things, but this time we mixed them together. Ugh. So how can we address this question? Well, what we can do is, I told you, it's all about the mole. Exactly. So what we can do is we can calculate how many moles do we have in here and how many moles do we have in here. Yeah? Let's do the first one. Let's say we have 3 milliliter of 10 micromolar solution. 10 micromole I can write as mole per liter. So, I want to find out the moles. Do I have moles anywhere? Yep, obviously. I have 10 times 10 to the, what is micro? What? Minus 6. Oh, thank you. 10 to the minus 6 mole per liter times, the mole is good, but I want to get rid of the liter. Do I have liters anywhere? I have 3 times 10 to the minus 3 liters. The minus 3 is the milli. Liters cancel out. And I've got, if I do the calculation, what do I get? 30 times 10 to the minus 6 mole. Yeah? Happy with that? Minus 9, thank you. I was just checking if anyone is awake. Okay, now I do that for the other one, for the 1 milliliter of 30 micromolar. Do the same thing. I have 30 times 10 to the minus 6 mole per liter times 1 times 10 to the minus 3 liter. What does that give me? It's the same thing, isn't it? I have 30 times 10 to the minus 9 mole. Sorry? Yes, you are absolutely right. We have 3 times 10 to the minus 8 or 30 times 10 to the minus 9. You are absolutely right. I really should do 3 times 10 to the minus 8, but I'm lazy today. Actually, there's a reason behind it. Because I can write this as, what is 10 to the minus 9? Nano. So I can write this as 30 nanomole. Yeah? That's why I haven't converted it. And that gives the same thing, 30 nanomole. Yeah? So if I mix both solutions together, how many moles do I have together? I have 60 nanomoles. Yeah? Happy with that? 60 nanomoles. What is my total volume? Total volume is 3 milliliter plus 1 milliliter. Yeah? It's 4 milliliters. Make sense? So I have 60 nanomole in 4 milliliters. $60 divided by 4, I don't need a calculator for that. I think I can do that in my head. That is 15 times 10 to the minus 9 mole per, I've just done that, per 1 times 10 to the minus 3 liters. Yeah? Which gives me, I can cancel a little bit out, is 15 times 10 to the minus 6 mole per liter. Minus 6 is micro. So I have a 15 micromolar solution if I put these together. So here the trick was, let's look at the moles. It's all about the mole. Let's get the moles together, and also let's get the volume together and divide them. So I would assume that you will be able in a test to do a similar calculation. Can you do that? Bob the Builder.
Yes.
Thank you. Yes, we can. Have a lovely weekend, and I see you on Monday.